For the navigation simulation, we've implemented actuation noise into our simulation and also have specified our list of testing scenarios. So here you can see in our code, we have variables to control the probability of actuation noise and also magnitude. And actuation noise is just the kind of random rocks or obstructions that are unexpectedly moving our vehicle as we traverse the path, or potentially noise in the motors that cause our vehicle to either turn or like shift unexpectedly. So here's a demo of that with the noise magnified. In addition to the actuation noise, we've also listed out our full set of testing scenarios. So here we have two types of noise in the sensing and actuation. And we plan to test our control on kind of the full range of each of these types of noise. And also we have 4 different lines that we want to test on that are separated by their turn diameter. And so you can see that here. We're testing lines with a turn diameter from 1 foot here all the way up to 4 feet. And these are all drawn to scale, so we can just load these into the simulation and test with them. And 4 feet is the kind of maximum allowable turn diameter for our environment specifications. So ideally, we'd like to be able to navigate on this environment for sure, and then any kind of small, tighter turn radius we can do is a bonus. So that's what we have for our navigation. Next week, our drivetrain design should be finishing up, so we'll be able to implement the correct kinematics into our simulation and then do our final PID tuning. For the identification subsystem, we've been looking at this stopping distance problem. So the problem has to do with handling occluded asparagus. Our planned way of doing that was that once an asparagus was sensed, we'd stop the robot, harvest the asparagus, and then the laser sensor would be in line to see any occluded asparagus after we've harvested the initial one. However, the problem with that was we forgot to account for the stopping distance, which means that after asparagus is sensed, the laser sensor will move past the row of sensed asparagus when the vehicle stops. And even if we harvest the initially sensed asparagus, the laser sensor is now out of line and can't sense these occluded asparagus. So we brainstormed a couple of solutions. First is just an actuator to account for the stopping distance. However, we determined that this would be expensive in terms of cost and also development time for the mechanical team. So we decided not to go with this. Another solution is to try and fill the stopping distance with laser sensors. But the issue with this is that the minimum width of our laser sensor is greater than the minimum width of an asparagus. And so we actually can't kind of pack the sensors close enough together to ensure that all the asparagus will be sensed. So we determined that this is also not a feasible solution. So the solution we're going with is to have 4 spaced out laser sensors. Here we're making use of the density constraint on our asparagus, which means that there's a maximum of 4 asparagus per row. So we only need 4 laser sensors spaced out by a stopping distance. And after the first sensor senses an asparagus, we can simply harvest it and then continue driving forward and check if the second, third, and fourth sensors end up sensing any asparagus to account for the next 3 occluded asparagus. So yeah, that's our solution to the stopping distance problem.
For the mechanical side of the actuator team, we were evaluating 2 gantry mounting options. On the left is an option where there's a greater moment on the gantry, but it allows for a greater range of motion for the actuator to move up and down. On the right, the configuration produces a smaller moment on the gantry, but it results in a smaller range of motion for the actuator. We opted for the second configuration because although the range of motion is limited, we're able to adjust the geometry of the gantry to adequately produce the range of motion that's desired. We've also opted for retaining rings instead of shaft collars due to its slimmer profile and reduced weight for our collector.
Okay, moving on to the gantry subsystem. This week, we started integration with the actuator team for the prototype. As you can see, we've got some acrylic plates that we kind of just mounted to our linear actuator mounting block. We try to mount it as close as possible to minimize the moment generated. And as it stands, it's under the loading capacity of the linear actuator, but we're still going to do some testing. We also did some electronics testing with some of the parts that we received. Now we're just going to continue to be doing prototype assembly and testing throughout the next week or so.
Hi guys. So for the chassis update, we're mostly waiting for the prototype parts to show up so we can start assembling. Hopefully that'll be done before next week, just depending on when it arrives. But in the meantime, we've been working on the product. So here's a pretty rough sketch of what our product would look like. And the top right is what our prototype looks like. So you can kind of see the correlation. So the product will have like the drivetrain, and the gantry system is also significantly different because it has an additional axis of movement. Here are the rough dimensions and like a basic sketch of, because the chassis is going to interact the most with the drivetrain. Here's how we plan on mounting that drivetrain, the motors and the wheels and the gearbox onto the chassis. Additionally, we also, because we need to start selecting motors for the drivetrain system, we have a rough weight estimate for what the chassis weight will entail. This is very basic. It's 35 kilograms at the end, considering gantry, chassis, actuator, but this is also not accounting for electronics and motor, which is might be up to like 100 pounds. So I think a more accurate estimate since our last update was on the scale of 300 pounds. And right now we're selecting motors for that with drivetrain. So that is our chassis update. Thank you.
Our task this week for system electronics was determining which pieces of hardware we need in order to run our deep learning algorithm. And so we're going to need a Raspberry Pi. We'd prefer Raspberry Pi 4 instead of 3. I can tell you why in the next slide. Also USB webcam, and what's important is a Coral USB accelerator. So basically looking at the table here, having a high enough FPS is really important to be able to identify something on the move. So that's why we need a Raspberry Pi 4 with the accelerator.
She was checking up on me from the game. She was spitting in my ear. You would think that she knew me. Decided to cheat. Conversation.